Hi, it's Terry Dennery of the MathWorks. So in this video, we're going to take that data that we just got from our test and we're going to use it to tune up our simulation model for a DC motor. Okay, so we're going to come back to this model. And I added just a little bit, just an ability to kind of compare the simulation with the test. And so we'll take a look at that. All right, so let's run this. So we have precisely the response that we showed before. It reflects our chosen values for torque constant, stall torque and no load speed and damping coefficient and shaft inertia. Okay, and as I said, it doesn't really indicate our real motor, and we're going to see that as we compare the data in blue with the simulation value right there. So not only does it not compare, it's far off. Okay, and so to fix this, we're going to use a app called parameter estimation. And so what parameter estimation will do is take that experiment and compare it with the simulation and adjust our selected parameters until the best fit is found. That's the basic idea. All right. And so let me move this over here and let's get into what does it mean to take that experiment. So our experiment ultimately is logged in the form of angle, right? And so it's that angle versus time is what represents our experiment. And so I'm going to just kind of show you what that really comes down to in MATLAB terminology. But it's really, let's submit the two-column array of time in the first column, angle in the second, and we hit enter and we see these two columns right there. Right, so let's go ahead and do that. All right, we'll create our new experiment and we will just paste in what I just constructed. We will show a plot. We'll click on OK. And that quickly the data is in. Right, now the next thing to do is select our parameters. Right, and I click on this button and we're going to see a short list of available parameters. Right, that's kind of funny, my test. Oh, that's right, because I'm using it. So that's the one we will not select. But otherwise, we see the four. All right, and these are showing up on the short list because there is a Simulink block with a Simulink field that's assigned with a MATLAB variable with the names we're seeing in this list. And so that was done for shaft inertia, the no load speed, the stall torque, and the damping, and that's what we're going to choose. Okay, and this is an optimization. It relies on Simulink Design Optimization to do it. And like any good optimization tool, it's a good idea to constrain the search on some of your variables. And so with regard to shaft inertia, it turns out all these parameters, which have physical meaning, and my knowledge of the physics is that none of them could ever be zero or could be negative. So we'll put a lower limit of 0 for each of them. But it's about as simple as that. And that once we do this, our cost function has been created, and the optimization is almost exactly ready. I'd say it is ready, but I do want to add one more plot, and the plot I'm going to add is we're going to follow these parameter trajectories as the tool itself goes and searches for the best values that will make our simulation result fit the observed experiment as best as possible. Right, and so let's have it so that they both show up. Let's click on our estimate button and let's just observe this. Right, and so it's going to give us this little estimation progress report, which will kind of show how many times is it running the model and at what iteration are we at. So the number of runs of the model is going to be called F count. Right, and we're going to see that for the most part, each iteration will be 9 and has something to do with it perturbing each parameter a little bit positive, a little bit negative, and basically identifying the trajectory. And there's a methodology in optimization called steepest descent. And if you kind of follow what they call these steepest descents, it gets you to your minimum as quickly as possible. All right, so let me move this out of the way. And we'll see our first iteration is right there. And that's actually the result we already knew. Now it's operating on a better estimate that was found with the steepest descent approach. And you're going to see very rapidly we get much closer simulation results to what we observed. You can see the cost function itself reduced from 102 to 16. Now, there's quite a bit of definition for that cost function that I haven't investigated yet, and I don't think I really need to know. So, so I'm not going to really worry about it for right now. But okay, so let's let this run. And having done this a few times, I know it'll go through about 5 or 6 iterations, but it all takes place pretty quickly. And yeah, I think that the example itself kind of shows sort of why you want to have a simulation model, that you can essentially run through, well, we run through so far 35 simulations, 35 tests, you might say, to, in a matter of like a minute or so. Okay, so we'll let it run its course. And you can see that even after these first 3 iterations, we're doing quite well. I might as well kind of draw our attention to this first hump right here, which is kind of where we're not doing so well. And I'll just kind of remind you that if you looked at that open loop voltage sequence that we provided, that's a very small ramp, right? And essentially it's something that's kind of searching for that breaking point on your static friction. And since we're not really accounting for static friction in our model, that we're doing damping, but we're not really doing this thing that lets go very instantaneously like static friction would, that's the place we're not doing so well, right? And I think it's very good to acknowledge kind of things that are going quite well, which we are with these peaks, but also kind of recognize that, if things are moving, we're probably going to do pretty well. If things are kind of in a static condition, there's probably things that we should be a little bit concerned about, right? And that just to kind of finish this one up, let's bring the model back up. Well, I'm going to show this, okay, that each of those values, not only were they identified with better parameters, that the workspace was updated to reflect those. And so we'll see much bigger stall torque and no load speed. And so when we run this model now, we will see that same fit reflected in our scope here. So anyways, very useful capability. I'd say, kind of emphasizing what we do with Simulink, their ability to build really good first principle models, whether we know the differential equations or if we know kind of the physical description. We use a tool called Simscape to help us convert physical descriptions into good models. It's always a great thing to be able to tune those things up for those hard to know parameters based on theoretical basis to get those in there. All right, thank you.